Good morning. So the first speaker today is Jishi. He's going to talk about a spectral rigidity and joint integrability for Anosov systems on tori.
Thank you. Okay, first thing is like, because yesterday case say something about thought, and to me it's like I have been here like 10 years ago for the beyond uniform hypothesis, and I have also some memory about thought like I like to share to everyone. Actually, like I think I met Todd the first time is in 2009, like also the Beyond conference, like in Beijing, and I'm just the first year of my PhD students, and I'm the one like helped Todd to register in the hotel, and it's during that time like we arrange some trips during the weekends. But the thing is like at the first I think we want to try to arrange the trip, but you don't need to pay anything. But it turns out like we couldn't cover the things for the trip. So every time I met someone like to register, I will tell them, okay, we can arrange some trips, and then I will say, okay, you need to pay something. It's to me, I'm just a freshman, so I'm a little embarrassed to ask someone pay something. But when Todd comes and I say, okay, we arrange some trips, and Todd say nothing, but take the word. Okay, how much should I pay? Okay, I think you are so nice, man, and something. And okay, that's the first memory to me with Todd. And then like we are also like in here in bed level, and I think that's the time like I know that there are some amber are quite good for the jewelry and very beautiful, and my mother likes it a lot, so I try to find some shop to buy the amber. And when I ask for the reception like which there's a shop for these things, and Todd comes and say, okay, I also need to buy some amber for my wife. And okay, and so I say, okay, that's so nice. I go with him together and we find some shops and buy some amber together. That's the thing. And also like in Provo, and that's he helps me a lot to go there, and so that's arrange everything for us, and that's the memory like I like to share with Tom. So last year when I know this, it's truly sad to me, and he's so nice and so generous, great man. And okay, that's the thing I want to say about Todd, right? Okay. Now, okay, today I will talking in this in the 4 lectures. I will talk about the spectrum rigidity and the joint integrability for Anosov systems on tori. So basically, like the manifold would be just for on torus, like 3 torus and in high dimensional torus. And so in the first 3 lectures, I will mainly talking about the things about the Anosov diffeomorphisms. And in the 4th lecture, I will talking about Anosov maps, like 3111 and something related to the action of Anosov maps just on the 2 torus and some. So many of these works are joint work with Andre, and also like who he's my students with Shabo and I think Shabo and also Jinpeng. Okay. Okay. Let me see here which I can see. Okay. Okay, I think everyone is very familiar with the definition of Anosov diffeomorphisms, but I will still put it here. And okay, and so it's you will have a continuous invariant splitting. That's one is uniformly contracting, one is uniformly expanding. And then the most famous things is the Anosov map. That's 2111, and that's the linear one. So, and for Anosov diffeomorphisms, I think there are some still some open questions which I like to refer. Is that every Anosov diffeomorphisms to be transitive? And also, is that possible to get some topological classification of Anosov diffeomorphisms? As Smell conjectured, like that all the Anosov diffeomorphisms is like topological conjugate some a fine model of Anosov automorphisms on infinite Neo manifolds. That's all the examples we have already known. So, okay, and some old results of John Franks and Manning, that's every Anosov diffeomorphisms on the D torus is conjugate to its linear part. Okay, so you are topological conjugate to these things. And also, we know that every codimension 1 Anosov diffeom must be supported on D torus, such then it is topological conjugate to its linear parts. So that's the thing like we know like. But on the other hand, it seems like we almost don't know everything about the Anosov diffeomorphisms on the torus. But on the other hand, there are some also some delicate things which we don't know. For example, as I think like a results of Andre and Tom Farrell, which shows like if the dimension like the D is larger or equal than 10, that there are infinite many components of Anosov diffeomorphisms that's in the space of all diffeomorphisms on the D torus, because you will have different structure things. And so that makes like even in higher dimensions, a lot of things will be unknown. So, and during like, I prepare all these works, it turns out like I find out that in some sense, we still know very few things about even for Anosov diffeomorphisms on D torus. Okay, anyway, let's see. Okay. Now, I will just recall some definition of partial hyperbolicity. I think like Thomas yesterday gives the definition like is so you just know like you will that's diffeomorphism is partially hyperbolic if it is has a three continuous invariant bundles, like one is uniformly contracting, one is uniformly expanding, and then there is a center dominantly between them, and this structure gives like that's makes the examples of partially hyperbolic diffeomorphisms are much more than the examples of Anosov diffeomorphisms. And also, I just recall like something about absolutely partially hyperbolic. It's just like the contracting rate and expanding rate is uniformly gapped. It doesn't depend on the change of points. So that's the thing. I just recall here because we will need it later. Okay. Okay. Now, I think until now, everything is just some very simple definition and nothing else. Okay, and so for my talks, for the whole talks lectures, I think the main question for me is like, if you have a partially hyperbolic diffeomorphisms, and what happens if you try to constrain the joint integrability of stable and unstable bundles? I think most of the research for partially hyperbolic diffeo, especially in dimension 3, and I think everyone heard the talks of Thomas yesterday, is try to thinking about what happens about whether you have center stable or center unstable foliations. That is the thing whether you are dynamically coherent or not. And I think like Christian yesterday said is early because like in dimension 3 is Enrique's conjecture about how to classification about partially hyperbolic diffeomorphisms. Then it turns out there are a lot of examples like which are in some sense unexpected, even like in three torus by Federico Hanna and Raul, and also later the examples like by Andre, Christian, and Rafael, and later Andy, and about that's on the unit tangent bundle of surface. Okay, you will have a lot of examples, but all these things are studied in some sense about the integrability of center stable and center unstable. So that's the thing. And for me, it's something, okay, what happens to the joint integrability of stable and unstable? So as you know, like if you are jointly integrable, then you will have some foliations, right? For example, in dimension 3, you will have SU two-dimensional SU foliations. And this makes like you are not accessible, right? And we all know like accessibility plays a central role in the study of ergodicity of partially hyperbolic diffeomorphisms. Moreover, from now, and we actually know some results and from Dima and Amy, and they show like C1 open densely, like accessibility, C1 open densely in partially hyperbolic diffeomorphisms. And if you constrain higher regularities, and Federico, Raul, and Hannah, and they shows like that if you are center one-dimensional, then they are open densely, like most of these things are accessible. So there are also other results for center two-dimensional and things. And I think in some sense, it gives you that the thinking like is something like you or like most of partially hyperbolic systems should be accessible. So you couldn't be SU integrable. And so this makes you to think in some sense, what happens if you are SU integrable? Do you have some space? Because it will be tells you like, okay, it is some spatial structure here. Okay, so the main philosophy for us here is like, you have SU foliation, which is something in some sense rare, as I explained. So it means like your dynamics, like partially hyperbolic, And also it preserves some geometric structure, which is an SU foliation, which is rare. And it should implies like your dynamics also have some kind of dynamical rigidity, right? That's the thing. And we expected is something like, okay, if you are SU integrable, let's you have SU foliations, and then you should be in the center, you could expect it some rigidity in some sense. But that is just a philosophy, it's truly not totally equivalent. We will show more examples. But I think like, okay, that's the main philosophy for us. And in some sense, and we will show like in some cases, we truly get this philosophy and we truly prove these things. But in some senses, this is not correct, but it also may have something else. Okay, I think the first result is due to Federico, and he studied something. And in his thesis, I think it's 2005, in the paper of Anosov, he studied something about the ergodicity of pseudo Anosov center two-dimensional pseudo Anosov automorphisms of the d-torus. And this is a typical example, like in dimension 4. And I think this matrix first appears in the last page of the book of invariant manifolds by Hirsch-Schub. And okay, and when I say like I spent some time to read the book, and Charles told me, okay, that's the damn book. Okay, that's the thing. Okay, and that's the thing. And they asked in the last page of this book, and they asked whether this automorphisms it is stably ergodic or not. And I think like Federico actually proves that things. And also what he studied is something like and for this matrix, you can say like it is irreducible and also partially hyperbolic. It has a two-dimensional center and one stable, one-dimensional stable, one-dimensional unstable, and a two-dimensional center, which is a truly isometry. That is a complex rotation in the center. Okay, complex rotation. And in particularly, and you can say like all exponents, all the ergodic measures has zero center exponents in this setting. Okay, that is the automorphism. And then that's Federico proved like that just this is not the whole series, just a particular series, because he wanted to prove it is stably ergodic. What he proved is like he gives a dichotomy, either you are accessible and then, or this accessible will gives you the ergodicity of this neighborhood diffeomorphisms. And the other case is like he has the SU integrability. Okay, and in the SU integrability case, and he proves that if your S and U are jointly integrable, then you can find a homomorphism H, which is close to identity, and also C1, which is C1 smooth along the center direction, such that F and A is topologically conjugate. Okay, but the key point is like in the center, it is smooth. And we know like that for a original linear one, that in the center direction, it is a linear translation, right? So it is ergodic. And this, then you get like the smooth conjugacy along the center tells you like your F is actually essentially accessible. So then applying the essentially accessible, and he proves like the ergodicity, even you are SU integrable. So the main thing is like, you can say like, he needs some C22 close to A. And this because he used some KM method to get like the smooth conjugacy along the center. That is what Federico has done. And in this setting, you can say like the key point is like in original one, your center are isometries, just some rotation. So when you are close enough, very, very, very close, and your SU foliation are as smooth as you want. So this gives you like the ways like you can apply the KM method. That's the thing. And I think this is the first result, which tells you like if you have SU integrability, and it will gives you some center rigidity. That's the thing. So in particularly, and as I said, like in the spectral rigidity, that means all the center exponents of F is the same to the center exponents of A. Okay, that gives you like the spectral rigidity. Okay, that's the thing. I think that's the first result. That's about SU integrability. But in general, I think you couldn't expect that, because I can give you a reducible case. It's like let's A to be to 1, 1, 1, and we can string like a linear automorphism which is reducible. That is A power 2 and A, which acting on T4. So you can say like this example, the original F0, it is also partially hyperbolic, and you can split it into 4 bundles. And you can string any f, which is C1 close to A, and you know like that it is also Anosov, okay? And you can start the perturbation of original F0. It's like you can string that's A power 2, and you put F here. It is also an Anosov diffeomorphisms, and you get the split that's into 4 bundles. Okay, you split into 4 bundles, and these 4 bundles, and you can look at this system as like you can look at it also as partially hyperbolic, because you can respect this weak stable, this one to be whatever. This one to be the center bundle, and this is stable, and this is unstable. And also you may also constrain this one weak unstable to be the center bundle, and you can also constrain both of these two to be the center bundle. So in any way you can get different ways of partially hyperbolic. Okay, and you can say like in all these cases, all these 3 cases, the 3 ways you can string as to be partially hyperbolic, and it all has the SU integrability. Okay, it all has the SU integrability. But in this way, since your F is arbitrary, like you have no exponent rigidity in the weak stable and no exponent rigidity in the weak unstable. This tells you, okay, in some sense, like reducible, like you need something to be irreducible then to get something. And okay, I think, okay. Now I want to introduce my main series. So first, for the setting, I will considering some automorphisms, which is in GLDZ, like it satisfies some assumption which is crucial to me during the proof. It's like first you need to be irreducible, and I need to constrain to be hyperbolic. Okay, and also I assume like 2 eigenvalues of A have the same absolute values, then it must be complex conjugate complex numbers. So that means like you have some, if you have 2 eigenvalues, then they are in the same eigenspaces and they are conjugated in some sense. And it can be proved like this thing, such kind of A is in some sense generic. That means like for most of these automorphisms in GLDZ, and they satisfy these problems. And this has been actually proved in the paper of Andrew and Boris and Victoria Sebstoya, and it's some results, because you can show like the matrix like don't satisfy these generic properties. It is contained in some hypersurfaces. For example, let's make the simplest example, because in dimension 2, that is the simplest case, right? In dimension 2, like you are in GL2Z, and you satisfy this condition, just need to be hyperbolic. And then you must need like the absolute value of the trace of this matrix larger than 2. So all the matrix doesn't satisfy this assumption will contains in that the trace is equal to 2 or equal to positive -1 and positive or -2. So it's containing some hypersurfaces. In high dimension, you can get the same thing. Okay, so we can string such matrix, and now for this one, and you can say it is induced an Anosov automorphisms on the D torus, and you will get a finite dominant splitting, right? You can get because it is hyperbolic, you will have stable and unstable, and you know that you can get it finer and finer, such that on each bundle of the dominant splitting, it is either 1-dimensional or 2-dimensional. If you are 2-dimensional, you are some complex rotations times some homosety, right? That is the finite dominant splitting. So that is for the linear one for A. And so our first theory is constrain like the local rigidity, which means like we just constrain Anosov diffeomorphisms, which is close to A. And we will see what we can say something about the joint integrability. Irreducible, you can look at one is like you look at the characteristic polynomials, which is irreducible over Z, also irreducible over Q. That's the one thing. The other way you look at it, it's like that's when you look at the acting on the D torus, you don't have the invariant low dimensional torus. That's the other way. Just like the reducible example I told you, like it's T2 times T2, that's times action. So that is irreducible. Or equivalently, I think that's more important is like equivalently, you can say like every eigenspace, you look at every eigenspaces of A, like it generated a dense linear foliation like in the detours. Every space is dense, okay? Yeah. Okay, and so right now I can string some F, which is C2 smooth, which I'm needing something, and it's C1 close to A. So since you are C1 close and you need to be close, and then you will have the same dominant splitting with A, right? You have the same dominant splitting and all the dimensions are the same. And right now I can string the case where like your stable can split it into at least 2 bundles. You couldn't be the stable to be just 1-dimensional or 2-dimensional complex. You couldn't split, then that doesn't work. So I will just split the stable into 2 bundles. The first, the strong stable is from that's corresponding to the perturbation of eigenspaces from 1 to K. And then you will have the weak stable that is from K plus 1 to L. And then you have unstable, right? So in this sense, you can say like your F, you can see it is also partially hyperbolic, and you can have this is to be the center bundle. Okay, that is a center bundle, but it's still Anosov and it is weak stable. Okay, it is weak stable. Okay. Okay, our theorem is like, we assume like the automorphism A satisfies the generic properties we have said, and then we show like every F, which is C1 close to A, and we give 3 equivalent conditions. It's like, the first one is like F is SU integrable, and then the second one is like we have F have spectrum rigidity in the weak unstable bundle. That means like, you know, like your weak stable is split into like a radius from K plus 1 to L, that is L minus K subbundles. And we say like a spectrum rigid is if in every one of these bundles, like all the exponents of F in this bundle, all the exponents, that means like you can say, because you are Anosov, you can say like every periodic points in this bundle, and also you can say like is every ergodic measures in this bundle, like the exponents in this one is equal to the exponents, Lyapunov exponents of A in the corresponding bundles. That is like which we said about the spectrum rigidity. Okay, and third condition is like the conjugacy H, because you know like your F is conjugated to A by some homomorphism, which is zero close to identity. And this gives you like, okay, and we can tell you like the conjugacy is smooth along the weak stable bundle. Okay, here smooth is just C1 plus alpha. Okay, no more, just C1 plus alpha. Because all these bundles, you know, like the bundles are just order continuous. When you integrate, like the leaf is just C1 plus something. So you can expect it more. Okay, that is the main theory of our results. And basically it says like, that's you have something, if you have SU integrability, then along the center, you are something smooth. It is much similar to Federico's results, like for this thing. But the thing is like in Federico's results, as I said, he used something about KM theory, which because in the center for him is like you are just some isometry, is some rotation. So when you have these things, you have very, very strong center bunching, as strong as you want. So this makes you like, if you are SU integrable, your SU foliations can be as smooth as you want. And this gives you the way like you can play KM theory and to solve these problems. But right now for us, because we are Anosov, our A is Anosov, so you will have some contracting in the weak stable. So this makes you like, in general, you don't have any smoothness of the SU foliation, even it is integrable. Okay, even it is integrable, you don't have any smoothness, so you couldn't apply the KM theory here. Okay. And yeah, here is the thing. Okay, here is the thing. Yeah. Because like I split the stable into strong stable and the weak stable. So k+1 started from here. That's the place we split. Yeah. Okay. So that means like, okay, maybe look at this one is much clearly. Yes. So that means like if you have this one together, because this one together, you know, like it is integrable because you have stable manifold theory. And this two is, okay. I don't draw that. Okay. Oh, no. Okay, we have the unstable, and this is also like integrable. And what we say is like your stable, strong stable, and unstable are jointly integrable, and it gives you like in the weak stable, every bundle, it is you have spectrum rigidity. That's exponents are the same with the linear one. Okay. Okay. And I think that's the thing is for higher dimensions. And let me recall something, what happens for in dimension 3. And that's the everything comes from. That's where we begin. Because the question is actually that people try to prove like the ergodicity of 3-dimensional DA, partially hyperbolic DA diffeomorphisms. And I think it's early, like almost 10 years ago, like Andy and Raul, they try to show like every DA diffeomorphisms, like on the 3 torus, when it is conservative, then it is ergodic. And in this case, like it's the general way is like to show like it is accessible, or otherwise you have something. And Andy told me like they have tried a lot, and they show like either F is accessible, then it is ergodic, or it has an F invariant minimal foliation, which is FSU, and such, which is tangent to the stable and unstable bundles. And also they show like that in this case, F is topologically conjugate to its linear part. But the only thing here is like, you know, like even you are topological conjugated to Anosov, but the conjugation is not absolute continuous. So you couldn't get the ergodicity from the ergodicity of the linear parts. So that's the thing. And also, even you are topological conjugated, like in the center direction, you don't know. Maybe you are not, for example, if the original one is linear part is contracting, but for the topological conjugator, that's for your partially hyperbolic diffuse, like in the center, you may just to be topological contract. So you don't have anything for these things. And then, okay. And he told me, like when I talked to him, he told me, okay, we should name this paper to be, I try to prove the ergodicity of DA diffeomorphisms, and I get everything except this one. Okay. Okay, and he then later with Chabot, like we prove like that in this setting, we have partially hyperbolic DA, and we show like your stable and unstable are jointly integrable is equivalent to like you have spectrum rigidity, like in the center direction. So that means like but of course we are based on the previous work of Raul and Andy and about these things, and we use something about topological conjugated to Anosov things. And we try to show like that's SU integral is equivalent to the spectrum rigidity in the center direction for the partially hyperbolic F. And in particularly, you can say like, if you have the center exponents, which every ergodic measures is equal to the linear part. Oh, here the linear part, like the center must be uniformly contracting or uniformly expanding. Anyway, so this tells you, okay, like both implies that your partially hyperbolic diffuse F is Anosov. Okay, that means like if you are SU integrable, then you are Anosov. And we all know, like from the classical results of Anosov, like in this case, like if you are conservative and you are Anosov and C1 plus alpha, will gives you like, okay, you are ergodic. So one corollary for these things is like every C1 plus partially hyperbolic DA diffuse is ergodic. That's the thing, like what happens in dimension 3. That's the earliest work. But then we will try to look at what happens in the higher dimension case. Okay. Okay, the first thing is like I give 3 items, like the SU integrable or spectrum rigidity in the weak stable or smooth conjugate in the weak stable. Actually, for the parts like to prove like spectrum rigidity implies joint integrability is some previous work by Andre and also by Andre with Boris and Victoria. And actually what they do is try to, all these works, they are trying to show some. Another question is about like if at every periodic points you have the periodic data, That means like the derivative at periodic points is conjugated to the linear part, whether your Anosov diffeel is smooth conjugated to the linear one. That's the thing what they study. But during the study, they actually show these things like if you have it's also some induction. Okay, sorry, I will write here. Okay, you will have splits. Okay, S1 plus ESK plus ESK plus 1 SL plus EU. And what they do is something like an induction, which shows like actually because when you have the exponents rigidity along ESL, and if you are one-dimensional and you can try to play some Lewis theory, and if you are two-dimensional, you can apply something about like the conformal structure introduced by Victoria and Boris, and to show like actually you are smooth conjugate in this bundle. Okay, you can show like this one because this one will gives you a foliation, and you can show like this is one is it is a smooth conjugate, and you can play induction if you have this one smooth conjugate gate, and then you I will write one more SL minus 1, and you can to show like in this bundle it is spectrum rigidity, and tells you like okay you can have the smooth conjugate in the lower one, that's is smooth conjugate in this one, and you play induction step by step until to this one. When you have all these things to be smooth conjugate, and it tells you okay you will map this foliation, this because you will have a bistable manifold theory which by strong stable, and you can show like this one will to be the linear one. That is a strong stable foliation for A. So, and you know, like you always have the weak, which is equal to the linear one. So these two are linear one, so are jointly integrable. And this makes you, okay, these two are jointly integrable. So that's the rough idea. I will not go through details about this part because that is some old things, but okay. Okay, but the thing is like, okay, that is how do you get spectrum rigidity to the joint integrability. And for most of this talk, of these lectures, I will try to explain how could you get from joint integrability, that's the geometric structure, to get the rigidity in the dynamic structure. Okay, so the picture is like this. You can see everyone can see the picture. That means like actually we show like SU integral will gives you like the conjugacy preserves the strong stable foliation and preserves the unstable foliation. And if you preserve these two things, and the whole thing in the center, in the weak stable, as being preserved is something, but this preserve means like is something smooth preserved. That means like your F, like in the weak stable bundle, the action will look exactly the same like the action of A. That's the linear part. That's the thing. Okay, that gives you the global picture for these things. Okay, I will give the main idea for the proof. Here is the thing. Okay, when you have the strong stable and the unstable to be jointly integrable, then it gets the spectrum rigidity in the weak stable. So the first thing is like we will show like if your strong stable and unstable are integrable, then the conjugacy preserves the strong stable. That means it maps the strong stable of F to the strong stable of A. I think it's something recently, there are a lot of works like try to show like about the minimality of the strong stable foliation. But I think it's something more because they try to constrain in the inverse of F, that's the minimality of unstable. I think it's a work of C1, Amy, and Rafael, I'm not so sure. And also is something like to show like whether the UU states is equal to the SRB states. And I think it's some work of Martin and Bruno, and also gives these things. But in this setting, it is something because like in general, you have no information about the strong stable foliation. You know nothing about that. You don't know it is minimal or not. and you don't, and in general, you couldn't expect it like the conjugacy preserve it. Okay, the conjugacy usually preserves the center foliation, but the strong foliation, or in other words, it preserves some foliation which is normally hyperbolic. But if you look at the strong stable foliation, it is not normally hyperbolic. In general, it is not preserved at all. So the first thing is like, we will show like if your strong stable and unstable are jointly integrable, then that's H maps the strong stable to the strong stable. That's the thing. And when we get this match, and then we know like we will have some quantitative estimation about how density of the strong stable foliations of A. So, and we know like the conjugacy H usually is order continuous, and it gives us some estimation about how the density is how the density of the strong stable foliations, and this gives us like the spectral rigidity in ES K plus 1. That is the thing. And then we will show like show these things like the strong stable integral with SK plus 1 and with U is integral. And we look at these things, these things as a new strong stable, and we play the induction. That's the idea. Okay. Okay, so the first thing is like we can show like the conjugacy preserve the center foliation. I think it's something very, very classical. So I just go through it quickly. And it seems like because the center foliation, you can say it is something normally hyperbolic. Okay, normally hyperbolic. You will, then you can original one for the linear one because it is smooth, and you can apply the work of Hirsch-Pugh to show like you always have center foliations because the original one is expensive. And then actually it tells you like no matter it is integrable, moreover, it is preserved by the conjugacy. The proof is just to look at the growth rate in some sense, because we know like in this case, like you know that you have the foliation, and that is a strong stable, weak stable, and this unstable, that is for your F. And you know, okay, here, you know, for your A, it will also have the strong stable and the unstable, and it's the weak stable. And you just try to look at the growth rate, and because in the universal cover, and because it grows very fast, iterated by negatively. Okay, you look at it iterated negatively, and you can say like in the weak stable is something like at 2 points in the weak stable, you will grow it a little bit, it will grow exponentially, but not so fast. Okay, not so fast in these things. It will in this direction, or not in the weak stable, but in here, you see like you iterate negatively, this will separate very, very fast. And for the linear one, it is also like that. When you are close enough, and you can say like actually your edge is preserves like the center, the weak stable foliations for every one of them. Okay, it's just some estimation about the growth rate in the universal cover. And you know like your edge is actually uniformly bounded with identity. And if you are close to your F is close to A, then this is actually H is C0 close to identity. Okay, that is the thing. You preserve your H, preserve the center foliation. No matter it just preserve the center. Okay. The second thing, it is something like about the linear foliation. And the linear foliation is like something like, which this lemma is something crucial to us. It's like, it tells you like, if you have a C0 foliation on the D torus, and like it is subfoliated by a linear and a minimal foliation. Okay, linear and a minimal foliation, then your foliation, C0 foliation is minimal and a linear. Okay, that means you have a foliation, maybe not linear, but if you subfoliated something by irrational, for example, irrational ones, like it is minimal and linear inside, then your large foliation is also linear and minimal. I think the minimal part is almost obvious, right? Because every leaf is dense. And then you try to play something. You try to look at this foliation, like you try to lift it on the universal cover, and you try to prove that the leaf of this big foliation, like path 0, it is closed on the addition, and is closed take the inverse. Then it tells you, okay, it is a linear subset space, and this tells you, okay, this foliation, it is linear. Okay, right now I take any 2 points, and we can show like this for xy belongs to this foliation, and it will have some Vn, which is in the linear foliation, but also contains in the big foliation F. And you can take a Kn which belongs to Zd, and such that your Kn plus Vn converge to X. And this is because like your Ln is linear and is also minimal. Okay, it's minimal, so you can take these things. And you know that your F is subfoliated by L, and L is linear, implies your Y plus Kn plus Vn. And you know that it is contained in this one. This is F. Why did you do that? Because you know, like here your F is like this. Okay, I will draw. F is like this. And it's subfoliated by some L, which is linear. That's your F. Okay, and this is your L. So, and you know, like your L is something linear. So you look at your Vn here, it belongs to L0. So you have like this point is Y plus Kn plus Vn, and this point will be Y plus Kn. Okay, because this one is Vn, so linear. So this tells you this point belongs to Y plus Kn. And you know, on the other hand, you know Y belongs to F tilde 0, and Kn is an integer. So that's the foliation in the universal cover is Zd periodic. So it will also equals to this one, and Kn plus is equal to Kn plus Vn. The same arguments here. So you can plus Vn here. And this tells you, then you can take n tends to infinite, and this gives you like this F0 is closed in the addition. Okay, that gives you thing. And similarly, you can prove like it is also if X belongs to the F tilde 0, and also implies like minus X also belongs to F0. So it's a closed connected subgroup. So it must be a linear one. Okay, that's the thing. So this thing will be used repeatedly in the rest of these things. Okay, and you can say that the next thing is like if you are your S and unstable are jointly integrable, then you will have it maps that's the strong stable foliation of F to the strong stable foliation of A. Okay, that matches the linear parts. The proof is quite easy because right now your FSU is subfoliated by the unstable foliation, and you know like unstable foliation is a minimal and a linear. So that means like your SU foliation after conjugacy, it is minimal and linear, and it's also A invariant. So and moreover, it is transverse. This one is transverse to the weak stable foliation, right? So it is transverse to the weak stable, and it's also A invariant. This makes you like it must equal to the linear SU foliations. Okay, so because for your A, you are Anosov, you don't have too many choice for the linear invariant subspaces. So you must match everything. And this tells you, okay, like your strong stable foliation after the conjugacy, it is equal to the linear strong stable foliations. That's the thing. So basically, until right now, the thing is like tells you like, okay, if you are SU integrable, then your strong stable must matches by the conjugacy to the linear one. Okay. And also in this case, you can tell you like if your strong stable matches, then in everything about K until K plus 1, sorry, here, if this foliation, this one to the linear, and it tells you, okay, everything here, sorry, here is from K, not from K plus 1. You can also get thing from K to K plus 1 and to L. It's everyone is matches to the linear. Okay, please note that every one of these things is integrable because like you in these parts, you can apply that it is a stable manifold theory. And in these parts, you know, like it is normally hyperbolic. You can apply the work of Hirsch-Puch. So this two foliation jointly to this one. So everything in the center continuously, it is integrable. Okay, and so this tells you, okay, right now come back to this thing is like if this strong stable matches to the linear, then this one, everything until L, it's all matches to the linear one. Okay. Yes, I need that thing. It's truly close. Yeah. It's to the things. I need to because I need some spectral gaps in here. like in F in this in everything k plus 1 is strictly smaller than k plus 2. Otherwise, I couldn't get the conjugacy preserve the center foliation. I think the thing is like you can assume the things like maybe not so close, you can get the same thing, but you need like you have a path with the same dominant splitting and isotopy to the linear one. Yes, that could be expected. Yes, that's right. But you need a path. Without this path, without these things, you get nothing. Okay. Yeah. And so right now is something tells you, okay, in particularly, if you look at K, this place, and you know, like if this one to the linear, okay, if this one to the linear, and you know, like your unstable after conjugacy is also to the linear. So it tells you like these two are integrable also, because if you maps to the linear, then you are jointly integrable. That's the thing, these two. Okay, these two are jointly integrable because like strong stable to the linear implies this K to the linear, and the linear one are jointly integrable. That's the obvious thing. Okay. So the proof is also the same, is also repeatedly use the fact like some foliation subfoliated by some minimal and a linear one, then it is a minimal and a linear. And right now you can look at something contains like from 1 to j. Right now I will put something like this, from this one to this one. It is a foliation, right? It is subfoliated by this smaller one, strong stable. And this strong stable one is minimal and linear after conjugacy. So this big foliation, that is what I write F as 1 to j after conjugacy, this one. Yeah, I right here. And this one is a minimal linear and also A invariant. And also you have, it is transverse. It is transverse to the rest part in the stable. And the rest part is to the linear one. So this thing must to be linear and also have the conjugacy. So you will get these things and you intersect and gives you like everyone, like here, you take the intersection, like FSJ, your maps to the linear one. Okay, it's just some repeatedly use observation that's all this happens. Okay, and the fourth thing is something you have the defending approximation of the strong stable foliations. I think that's something you can expect it because it's something, you know, like your H maps the strong stable of F to the strong stable of A, and your H is order continuous. So you just need some density estimation of the linear one. But for the density estimation, it is irreducible and it is algebraic. So it will gives you thing. And you just try to look at it in two different ways. One is like you have one-dimensional real subspaces, and you can look at it as a flow, right? You can look at it as a flow, and you look at the transverse torus. And if you don't have one-dimensional one, you need to look at some algebraic Z2 action, and the proof is the same. Okay, some different things you can expect it for the algebraic one. Okay. And right now, I will begin to prove like the spectrum rigidity, like in the K plus 1. So I will taking two periodic points because here you are something like because you are Anosov, so you can take some periodic points which with different if you have periodic points with different eigen exponents, and you okay. First we look at that. That's K plus 1 is one-dimensional, okay? Then you can take some periodic points, which is minimal, almost minimal, and almost maximal. And okay, and then you try to take the things, okay? Try to look at segments, take some points. Here is the thing. Okay, I will take the picture. I will take some P here, which is in the weak stable, is contracting the strongest one, that is K plus 1. And also I have some Q, maybe Q here, like in the weak, in this center, K plus 1 is something weaker. The contracting is the weakest one. So right now I look at strong stable foliation. Okay, I put it very stronger. And we know like it is very dense and we have some quantitative estimation. So I can took some points X and here, that is here the distance will be kn very large, and here the distance will be c times k, and it's alpha. So that's power minus alpha. So something very smaller here, and I want to show something. Okay, I will first of all, I will take some j here. Okay, I will take some small segments here. These small segments, the contracting rate will almost like the contracting rate of P, right? Because when you are close, your contracting rate is the same with P. And then you look at the holonomy maps, okay? You take that Jn to be here, Jn to be here, which is deduced from the holonomy map of strong stable foliations. Strong stable foliations. And you, in this place, and you can say like the key point is like your strong stable after conjugacy is to the linear one. So basically you can look at the picture after conjugacy, after your H, it is linear one, okay? So that is your Hj, and this is linear. Okay. This is Hjn. No matter how far of x, okay, sorry, this is Hxn, which is Hp. No matter how far of these things, these two have the same length. So this tells you like your Jn has some estimate about like the length. It couldn't to be 10 to 0, no matter how far it goes. No matter how far it goes, it's uniformly bounced by something. And the thing is like this. Right now, you have some estimation about this J, how this grows after iteration. It will contracting rate like the exponents of P, right? And for this Jn, what I want to show you is like it's very close to Q. So you can look at some first the Kn steps. They are also close. Okay, as that's Fkn of Jn. And that is, I will put Q here, Fkn of Q. So they are also very close. This close makes you like that's the first Kn steps. And also, and then you iterate more and more, Fkn, and then you iterate more to Fmn, like this Jn to be something very smaller, like to be here. That's the first time with length to be 1. So that is something of Fmn of Jn. And here you also have like Fmn of J. Okay, so you iterate it like this. And you can tell us like something like you can estimate the growth rate of Jn is like in the first Kn step, the contracting rate is almost like the contracting rate of Q, which is weaker than P, right? Which is weaker than P. And for the rest part, the contracting rate is at the most P, because P is the strongest contracting in the whole manifolds. So the rest, this part, this Kn steps is like Q, and for the rest, it will be the same with P. But for J, it will always like P. And what you need to do is like you use the differential approximation to tell you like, okay, this Kn steps has a positive proportion to Mn. Okay, positive proportion of Mn. And this gives you, okay, and we have the estimation about the growth rate, and it tells you like, okay, for Kn tends to infinite, like Kn will tend to infinite, and Mn will also tends to infinite. And this is a positive proportion and tells you, okay, we have the growth rate must tend to infinite. That tells you, okay, your holonomy maps to here is also the strong stable holonomy from Fmn to J to Fmn of Jn to holonomy to here. Okay. However, this is also the holonomy map. But on the other hand, you know, like it's some results from about Hodel foliation in the paper of Hodel foliation by Amy, Charles, and McShoop, like tells you, okay, actually this foliation, like the strong stable foliation, restricted to the foliation of F strong stable plus stable of K plus 1, it is C1 smooth, uniformly C1 smooth. And this is a contradiction, because here I tells you like the holonomy is tends to infinite. So that's a contradiction. Okay, that is the thing. That is for one-dimensional argument. Okay, that's actually the picture I drew here, but I couldn't put it every page. That's the thing. Okay, so here the key point, I think there's two things. First thing is like the J, no matter holonomy how far goes, that is uniformly bounded from zero. That's the crucial part. And also you have the diffeomorphism approximation tells you, okay, your Kn times is positive proportional to Mn times, uniformly bounded, uniformly proportional. Okay, that is from the thing. Okay, and for if you are two-dimensional things, you can do the same arguments, almost the same. The only difference is like here is not a segment anymore. Here is something. This one? No. I can use it. It's the same, but the only difference is like you look at the disk anymore, and you look at the holonomy of something, and that is your P, and that is your Q. You do the same arguments, but separately. The first thing is like you look at the minimal, because here you have a two-dimensional things. You have two exponents. You can look at the smallest one. That's the same arguments, but here is a little bit cheating. It's not so easy. I will talk more about this in the next talk because here is something difficult, but the thing is the same. You can estimate the smallest exponents in the two-dimensional bundles. And also you can estimate the growth rate of area. You look at the area because your holonomy puts to here, you have a disk and you have a disk. And when you're close to Q has some contracting rate here. And you can prove like for every periodic points, every pair of periodic points, like the Jacobian on the two-dimensional bundle of K plus 1 has the same Jacobian. Okay, so you know like the minimal one everywhere is equal, and the Jacobian, that means the sum of two exponents are the same. And this tells you, okay, that's a picture. Everything is the same, just repeat the argument. You have a diffeomorphism approximation and you have the same estimation, the same thing. And it tells you, okay, and since you are close to A, so in the 0 point, you know like you have some rotation. When you F are close to A, you are also rotation in some sense. So these two exponents must be the same, and it tells you, okay, everything is the same, have the same exponents everywhere for F. But you need some more arguments to show like it is actually equal to A, because you need some volume growth, and you know like F sk plus 1, here this one is to this one. And you can show like it's actually equal by some growth rate in RD, in the universal cover. Thus exponents must be equal, Not only everywhere is equal on the for F, but also equal to A. That is something. Yes, and so finally, right now, I think until here, we finish to prove the spectrum rigidity in ESK plus 1. That is the thing. And right now I can prove by play some induction is like we look at the strong stable and until joint with the K plus 1. This is the thing. And we know like it is linear. And so linear one is always jointly integrable with the linear one, which is the linear unstable foliations. Okay, they are jointly integrable. And so it's just like this. And so that tells you that this two originally is this thing jointly integrable with these things. Right now, we already know we have spectrum rigidity with this one. And we know like this is a minimal subfoliated these two together. So right now I can put these two together and we show like it is actually a linear one. So this thing is jointly integrable also with unstable. Okay, we have also it is jointly integrable with this unstable foliation. And so, okay, I can look at this thing, okay, ESK plus 2, and we can look at this one as the new weak stable, okay? The new weak stable, and play the same argument to get the spectrum rigidity in K plus 2. Oh, okay, in K plus 2. And this gives you, okay, I can play the induction step by step until to L. Yes, L. Okay, this gives the proof of theorem 1. Okay, and I think I will stop here. Thank you.
There are questions or comments?
Oh, please. What? Sorry.
Yes, so you required like the spectrums to be of dimension 1 or 2.
Yeah.
Yeah, so you can do that same argument for higher dimension.
Oh, the thing. Okay, that's a good question. And actually, like in some sense, like for when you are close, I couldn't handle the things because I need some complex things. For example, if I have eigenvalues for lambda and a minus lambda, it's a little bit difficult because it will have one dimension things doesn't works. But in another situation, which I will talking tomorrow about the global rigidity, I can handle this problem, but I need some further assumption about central bunching conditions. And in the next talk, I will talking something about like for Anosov diffeomorphisms, which is not close to the linear one. So it is also some global rigidity. And I will begin with something about the four-leaf conjugate and then spectrum rigidity things. Yes, but I can handle in some sense, but need to pay the price that is some center bunching assumption. I will show later tomorrow. Yeah, thank you for the question.
More questions? Okay, let's thank the speaker again.
Thank you. Thank you, everyone.
And now there are some announcements. Please wait.
Thank you. Thank you. So if you need a transport to Poznań on weekend, then please sign up for it today, because tomorrow we close the list and we need to organize everything. The list is just on the desk where we had the registration in front of this lecture room. And similarly, if you want to use the conference bus from Poznań railway station to Bendlewo on Sunday at 5:45 p.m., also please sign up for it today. Okay, thank you. Enjoy the coffee.